Well, all right, now we are in the middle of section 5.2, and this video, hopefully it's kind of short, will describe some more of the properties of the definite integral. But these properties are just going to be so important to you, you're just going to want to make it second nature as you go through the problems. You can't help but have that happen as you do the homework we're about to do. Okay, so we're talking about the definite integral, and this next property says the integral of a sum is equal to the sum of the integrals. Well, actually, it's the sum of a function plus another function. Okay, if you're integrating the sum or difference of a function, and another function, you can split them up into two separate, definite integrals. And the question would be like, why? Okay, so let's show you. I can do it generally. Okay, let's do it generally. Let's say we're looking at the integral from a to b of some function plus another function like so. Okay, by definition, what this means is we're looking at the lim, if it exists, as n goes to infinity, of the sum as I counts from 1 to n of the function evaluated at x sub I star. Well, this particular function is f of x sub I star plus g of x sub I star. And then you multiply it by delta x, okay? Well, wouldn't you know that what you could do is you can distribute that delta x inside for every term, right? Remember we had in an earlier problem, we had 0.5 was my delta x, and it was multiplying with all the functions in there. I factored it out. Well, you can put it back in, okay? And we're doing it right now. So we're looking at summation lim. So it's equal to lim as n goes to infinity. And I'll write it as f of x sub I star times delta x plus g of x sub I star times delta x. And it's not like a major proof or anything. But if you think of these terms, what you're seeing is you're going like, well, okay, I is equal to 1 to n. What you've got is like, I got the first guy as f of x sub 1 star times delta x, and then plus f of x sub 2 star times delta x, plus all the way down you get through all the f's, and then you get to the g's, and you've got, I'm doing it wrong. I'm sorry. That's where I want to go. What I've got is plus this guy, okay, delta x, plus g of x1 star times delta x plus, and it goes on and on. But who says you have to do it in that order? Because of the associativity of arithmetic, you can simply go, I'll put all the f's together, f of x1 star delta x, that's the area of one rectangle, and then plus the area of the other rectangle under only f, x sub 2 star delta x plus dot dot dot, and then you get to the g's, g of x sub 1 star delta x plus, etc. In other words, you can split them apart and write it as lim n goes to infinity of basically this. You can go, I can split them up as two different sums, I equals 1 to n f of x sub I star delta x, and then the other summation I equals 1 to n, and it's g of x sub I star times delta x. And of course that means it's the same thing as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Now you can explain that in different ways. I took the notation route, but a person can come along and go, hey man, there's a picture. Let's say that this is f. And let's say that, well, make it a little lower. Let's say that this is f like that. And then here you have g. Okay, make him another color maybe. Okay, so g is doing that. So what does f of plus g look like? Well, okay, let's do that in red. Not to belabor this. It's kind of fun to play though. One of the rectangles would be, okay, there is a rectangle under f, and then here's another, it's the same rectangle, a different rectangle under g, and if you add the functions together, you're going to be way up here somewhere, f plus g, and it just makes sense that if you add these two rectangles, this is what you get. All of a sudden you take the G rectangle, which is actually this tall, and tack it onto the F rectangle. You know what I mean? So there's a lot of different ways, but the main thing you're going to see is this. For instance, if you have an integral from 1 to 4, and it says, hey, I want x squared plus 2x, that's what I want. This particular idea allows us, and it's an important one, it allows us to split it apart, 1 to 4, x squared dx, and then the next one, integral 1 to 4, 2x dx. And you're on your way. You can split it into integrals like that. Next semester in Calc 2, I have to remind people that you're able to do this because of the sigma notation. You're able to do what we did up here. Like, okay, the associative property allows us to do that. So that's a good one to have. Here's another one that's really cool. It says the interval of integration can be broken into pieces. That's my wording. Okay, so here you got your typical, here's f, and someone says integrate from a to b, but for some reason, maybe there's an asymptote or maybe something is in the way, there's a reason that you're going to maybe think about doing this particular move right here. That is to say, pick a c in the middle and drop it down, okay? And what this is saying is if I integrate from, say, a to c, this function, now think in terms of areas, it'll take care of that area, okay? Plus, if I integrate from c to b, same function, that'll take care of the rest of the area, right? Think of it in terms of areas. And so basically, if I add those two areas, I get the entire area from a to b, do I not? So does that make sense? I'm adding this plus this. A to c, c to b gives you a to b. Isn't that interesting? The function has to be continuous for that to happen. There are times when you have to do that, and when we see them, we'll see them. We'll have to break an integral into two pieces. I think of a couple different cases in the future. All right, here's the other three. So this one says, going to be kind of obvious to see the next three. They're pretty cool. It says, if a function is positive, then so is its integral. That is to say, if f is greater than 0, so is its integral. Does that make sense? So here's your function f traveling along like that, and he's always greater than 0. That is to say, he's above the x-axis. So guess what? The area is positive, isn't it? That's a pretty obvious one, is it not? You take this guy's rectangle, and what you're doing is you're figuring out the height by going f of x sub I star, and it's positive. We had a discussion in the last video about this, where you can have positive and negative areas, right? So this is saying if you're greater than 0, so is your integral. Over the interval, that is, say from a to b, right? Here's another one. This one applies to two different functions. So it goes, if a function is bigger, then so is its integral. If a function is bigger than another function, then its integral is bigger as well. And that, again, in pictures makes sense. You know, you have f traveling along, then you have underneath it maybe g, and if you're integrating from, say, a to b, and you notice that f is always bigger than g, then all of its rectangles are larger as well. So his integral from a to b is larger than the integral of g from a to b, right? So here is, boom, that's the height of his rectangle, and then you go over to this guy g, and he goes, that's the height of his little rectangle. You go, okay, when I sum up those little rectangular areas for g, the sum is smaller than the sum of the rectangles for f. Okay, so but then you take the limit if it exists, and the integral also is bigger. Make sense? And here's the last one. We'll actually do a homework problem from here. This property is saying, if you know a function is on an interval is bounded by two numbers, like a function is like always bigger than or equal to one number, but less than or equal to another, then what happens is you get kind of an estimate of the actual value of the integral. So what I chose to do in this case was look at a problem towards the end. I think it's problem number 60 in your text. Number 60 says this. It says, this is a theorem or property 8. Use this property. Okay. And it says in this case, to estimate the value of the integral. That's an interesting way to say it. To estimate the value of, and I'll put the integral down. It's the integral of 1 over 1 plus x, no, 1 over x plus 4. And the limits are, in this case, important. It's from 0 to 1, This is page 390, by the way. From 0 to 1, this is page 390. So it takes a little bit of knowledge to of the curve itself to know what's going on. This guy, of course, has a vertical asymptote at x is -4, but that I don't think is going to come into play, -4 there. Because they're asking us to integrate from 0 to 1, this region right here. So what is this function really doing? If you know what it's doing, then you're in great shape, because what happens is we happen to know that this function, what it does is it swoops down like this. It also has a piece over here, but we're interested in this picture right there, okay? What we're about to say is this is the highest this function is. Which function? The function that says f of x is 1 over x plus 4. Did I not make that clear? I apologize. That's your integrand. That's the function we're dealing with. So the highest it is right there, and the lowest it is right there. And those values are easy to compute. You simply go, what's f of 0? F of 0 is 1 over 0 plus 4 is 1/4. Okay, then what else? Oh, what is f of 1? Well, f of 1 is 1 over 1 plus 4, is that right? Is equal to 1/5. All right, so what we can say is the following. We can say, hey, you know what? 1 over x plus 4 is greater than or equal to 1/5, but then it's less than or equal to 1/4. So what does the property say? Well, it says, look what it says. And I can actually draw a picture of this, maybe a better one if I would like to draw a better picture than I have right now. I'm going to do some color on this one. It's saying that the area under the curve right there, okay, is actually less than or equal to the area under this rectangle. That's one way to say it. And greater than or equal to, say, the area under this rectangle here. So you got a green rectangular area, and then you got this other rectangular area even larger, and the blue area is in between. Well, what is the area of the larger rectangle? It is the height of the rectangle here, which is 1/4, times the interval here, which is 1. Okay, so the thing says, he goes, the integral from 0 to 1 of 1 over x plus 4 dx is bookended between, guess what? The minimum guy, 1/5, times the length of this interval, which is 1 minus 0. That's where I got the 1 right here. And then less than or equal to 1/4 times the length of that interval, 1 minus 0. So our conclusion is that, where can I put it? 1/5 is less than or equal to our integral, 0 to 1. You wouldn't believe how important some of this stuff ends up being sometimes. It's a clever little argument that once in a blue moon is useful. So the integral, we don't know what it is, but it's trapped between 1/5 and 1/4. That's a pretty good estimate. All right, so we'll come back with one more video with an example for you in this section. Thanks for listening.